Today we're going to start section 1.2, which is exploration with patterns. We've done a little bit with this already because we did Gauss's method, which was about patterns as well. So there's a little bit of this that's going to feel like we've already sort of embarked upon this journey. Okay, but we're going to go a lot further today. So to start with, we need some basic language so that we're all talking about the same thing. The first one is the word conjecture. A conjecture is a statement or a conclusion that has not been proven. It's a guess. That's what it really is. A conjecture is a guess, an educated guess usually, but it is a guess. A counterexample is something that proves the conjecture false. So anytime you see the word counterexample, and we will see that throughout this semester, counterexample means an example that shows something doesn't work. And there's two types of reasoning: inductive reasoning and deductive reasoning. Inductive reasoning is a method of making generalizations based on observations or patterns. And deductive reasoning is the use of mathematical axioms, theorems, definitions, or undefined terms assumed to be true for logic and proof. Inductive reasoning is what happened when you woke up this morning and you probably put on a heavy coat thinking it's going to be cold outside today because it's been cold outside yesterday or the day before. You're making a generalization about what happens today based on something that happened yesterday, the day before. Okay, we do it all the time. Deductive reasoning would be waking up and looking at your weather app on your phone or on the news or whatever it is, however you get your information, and you say, oh, but it's going to be 60 degrees later today, so yes, I can wear a short sleeve shirt. I don't need a jacket, or at least I don't need my heavy coat. Okay? That's deductive reasoning, using more information than just the establishment of patterns in the past. Okay, sequences are ordered arrangements of numbers, figures, or objects, and kids start working with sequences as early as pre-K. They usually use objects. So it'll say something like red triangle, yellow circle, red triangle, yellow circle, and it's just the pictures. And they say, what comes next in the pattern, right? Pattern recognition. That's a sequence. A recursive formula is a formula based on the patterns established after one or more consecutive terms are given, and a rule that shows how to obtain each successive term of the sequence. Okay? So this would be like starting a pattern saying, and it's usually done with numbers, but we're going to see an example later on that's not numbers, but they're usually numbers. And it says something like, the sequence starts with 4, and you get the next term by adding 2. So you get 4, 6, and you can continue the pattern, right? 8, 10, so forth, because you know the first number, and you know how we get the next pattern. You know the next number in the pattern. It's a recursive formula to get the rest of the sequence. You know how to get the next one. An nth or a general term is a formula used to find the nth term in the sequence with no prior terms needed. This usually looks like an equation. It says something like the numbers in the sequence follow this equation, 4x plus 2. So if x is equal to 0, the first term is 2. And if x is equal to 1, we can plug the number 1 in, and we can get the second term is 6. Okay? So it's an equation that you can use to get the next term. And it doesn't necessarily have to be the next term. It can be any term, and that's an actual really helpful piece based on this formula. So if you want the 50th term, and you have an equation, you just plug in 50 into it, and you find the 50th term. If you have the 50th term you're supposed to find, and you need only the recursive formula, you have to find out what is number 2, and number 3, and number 4, and number 5, all the way till you get to 50. Not such a happy thought, right? Okay, but that's the difference between those two methods. All right. Two types of sequences. First one, it's called arithmetic. An arithmetic sequence is a sequence where you use an addition or potentially a subtraction of a value to get from term to term. So for example, and we've seen this one already, Actually, I'll change it up a little bit. How about we do this one? That'll work. This would be an arithmetic sequence. Because what would I be adding to get to each of the next terms from the term before? 4. And because it's the same, that is, it's the same thing I would be adding, that makes this arithmetic. And that number that I added is actually got a name. It's called the common difference. Now you could add a negative number every time. That's okay too. So if I had a sequence like, well, I'll just flip it around. 14, 10, 6, 2. Eventually it would become negative, but what I'm adding every time is actually negative 4, right? You could also say you're subtracting 4, but we'd actually say we're adding negative 4, so the common difference would be negative 4. It would be a negative common difference. So you can have a negative common difference or a positive common difference. It's the number you're adding each time to get to the previous term, from the previous term to the successive term. Okay, so this is one type. The other type that we're going to look at is called a geometric sequence. And a geometric sequence is a sequence in which each successive term is obtained from the previous term by multiplying. And it says multiplication of division by a specific number. It's really multiplication, so I'll show you what happens when it sort of looks like division as well. So, an example. Let's say you had this one. What would you multiply by to get from one term to the next? It's 2 times 2. All right, so we would call 2 the common ratio. Okay, the ratio is the number you multiply to get the next term. Now, so what happens if it looks like division? Let me give you an example of one of those just so you can see the difference. Actually, let me move this one. Oh, I've got space over there. So here's another example. Let's say we have 108, 36, 12, 4. And obviously the numbers are getting smaller, so we're dividing. I mean, what are we dividing by? 3. So you're dividing by 3. I mean, definitely dividing by 3, no question. But we want to state the common difference, the common ratio in terms of a multiplication, like what am I multiplying by? So if you'll remember from back in the day, somewhere in middle school somewhere, somebody told you that dividing by 3 is the same as multiplying by 1/3. So we would say that the common ratio often is the letter R, would actually be 1/3 here. Okay, so we multiply by 1/3 because it's the same as dividing by 3. That's all we're doing. Sound good? Okay, so it's always in terms of addition, it's always in terms of multiplication, even if it's a negative that we're adding or a fraction that we're multiplying by. All right, there are other types of sequences. One more that I'm going to make mention of is going to be a Fibonacci sequence. Who's heard of Fibonacci sequence before? I'm not going to ask you what it is, just have you heard the phrase before? Okay, so about a third to a half of you have heard of what this is. This is non-arithmetic and non-geometric, and it follows a different pattern, but the pattern is common in nature. So let me show you what that pattern is and see if you can remember how you get from term to term. I'm just writing down a few of the terms, of course, because sequences are continual. They keep going. So this is a portion, or the first portion, of the Fibonacci sequence. And you can see it's not addition of something, right? I can't take 1 and add 1, anything to it besides 0 and get the next number 1, but then that doesn't work for the next value, right? So that doesn't work. Multiplication, same thing. I can't multiply by something and get these numbers to continue on their process or whatever. But does anybody now remember what you do?
You add the 2 previous terms to get the next one.
Yeah, you add 2 values, and so we'll just take these 2. If I add 5 and 8, I get 13, and that's the next term. And that is how we use the Fibonacci, or how the Fibonacci sequence is continued or extended. So if I were to want the next term after 21, it would mean I would add the 13 and the 21 together, which would give me 34. And then what if I wanted what's after 34? We'd add 21 and 34 together, and we would continue it. So 21 plus 34 would be 55. And we could keep that process going. So that's a Fibonacci sequence. All right, this definition feels so oddly placed here, but we need it in a minute, so that's why it's here, okay? A reminder of what exponents, or how exponents are defined. So the definition of a to the power of n. If n is a natural number, then a to the n means a times a times a times a n times. And Catherine was the one who came to ask me this morning, because we haven't discussed it yet either, to be sure. 0 is not a natural number. It's called a whole number, and we will get to this in chapter 3, I think, actually, before we actually talk about the language here. But we do need to know what happens when we have n equal to 0. Okay, it's not a natural number. So if n is equal to 0 and a is not equal to 0, then a to the n is equal to 1. It's equivalently saying that a to the 0 is 1. And for right now, we're going to take that to be a fact. If you haven't taken proportional and statistical reasoning yet, we prove that fact in proportional and statistical reasoning. But for what we're doing right now, we're going to assume that it's true. Okay? So that's all we need to really mess with in terms of the exponentials, and they're going to come up very soon. So here's where we're going to take a look at sequences. What we're going to do is we're going to go through 3 parts to each problem, list the next 3 terms, identify if it's arithmetic or geometric or neither, and then find the nth or the general term of the sequence. And that part I haven't shown you how to do yet at all. So I'm going to show you on these. The first 2 parts, I think you have an idea of what you should be doing. The first one says, list the next 3 terms. So taking a look at 1, 4, 7, 10, what comes next?
13.
And then?
16.
And then 19. So these are the next 3 terms. Fantastic, right? And how did you get those? You added 3. So the process here was an addition of 3 every time. And because the process was add 3, then is this arithmetic or geometric?
Arithmetic.
It is arithmetic. Okay. So really, steps 1 and 2 are very straightforward. Step 3, I need to show you how we develop this. So for those of you who've had me before, you know this about me, but for those of you who haven't, I'm not a huge fan of memorize a whole bunch of stuff. Because I feel like that if you memorize a whole bunch of stuff, you're going to memorize it for about 2 days, maybe not even, long enough to take a test, and then long enough to take the final again. Right? Probably a good majority of it, right? Because you're just not going to internalize it very long. So I'm a much bigger fan of teaching you how to think and reason through how to do a problem. Because that, hopefully, if we reason through things, will stick with you longer. So there's a formula for this, and it's in your book. I'm not a fan of formulas. So I'm going to show you how we reason through this. So let's go with it. The first thing to notice is that this is addition of 3 a whole bunch of times. So ignore the numbers that are here for a moment and just think with me for a moment, if you will. If you were to add 3 together, 3 plus 3 plus 3 plus 3 plus 3, a whole bunch of times, there's a faster way to do that. What's it called? Multiplication, right? Adding the same number together a whole bunch of times is really just multiplication. Agreed? So if I'm adding 3 together a whole bunch of times, and I know that these numbers, 1, 4, 7, and so forth, are not actually the number 3. I'll deal with that part in a minute. But the way I'm getting from term to term is a whole bunch of adding of 3's. That's multiplication. So our general term, or our nth term, is really taking the number 3 and multiplying it by n, the number of terms we have. But see, a general term is supposed to be if I plug in n equal to 0, I get the 0th term. That doesn't make sense. Let me do 1. If I plug in n equal to 1, I get the first term. If I plug in n equal to 2, I get the second term. But that doesn't quite work with this particular sequence, right? If I plug in n equal to 1, what do I get? 3. What am I supposed to be getting? 1, because 1 was the first term in my sequence. So what would I need to add or subtract to make it work? Subtract 2. And you can check it for the second term. What happens now if you plug in n equal to 2? 3 times 2 is 6 minus 2 is 4. Was that our second term? Yes, it was. And you could check a couple more of them if you'd like, but this will always work. Whatever your common ratio is creates a multiplication factor, because really all arithmetic sequences is repeated addition. It's multiplication. So you have your ratio times n. And then you just need to add or subtract the value at the end that makes it work for the first term. And you're done. Okay? You'll have plenty to practice on, but that's how it works for arithmetic. The second one's not arithmetic though, is it? It's not. So let's find the next one. The second term, or the second one, part B, what is it, fifth? The next term anyway. What's the next term in this sequence? 48. And then? Yeah, they get big pretty fast, don't they? And then what's after 96? 192. Some of you do multiplication pretty good in your head, huh? All right, and that's 1. All right, so this is step 1. Find the next 3 terms. We did that. All right, is it arithmetic or geometric?
Geometric.
It's geometric. What did you do to get from term to term?
Multiplied by 2.
You did. You multiplied by 2. So this is geometric. And it doesn't ask me to do this, but I'm just going to write it in just for a moment. Your R value, the ratio is 2, right? Whereas up here, the common difference, we usually call it D, was equal to 3. You don't have to write that down, but that's how we're actually creating the formula next anyway, so it was useful information for us. R equal to 2. Okay. So here's the deal. Whoops, that didn't look quite right. We multiplied by 2. And again. And again. Repeated addition is multiplication. Repeated multiplication gives me exponents. Right? 3 cubed means 3 times 3 times 3. So when I multiply 2 together 5 times, that's 2 to the 5th. So I'm getting exponents. So just like I used above 3 times n, here I'm going to use 2 because it's the number I'm multiplying, and it's raised to the n. Everybody okay? Of course, if I plug in n equal to 1 and it gave me the first term, I'd be done. But that doesn't work here, does it? If I plug in n equal to 1, I get 2, and I should be getting 3. And adding or subtracting here is not going to be helpful. But multiplying something is. So we have to do 2 things next. First thing is I don't want this to be n exactly. I want it to be n minus 1. I'll explain why, but give me a minute. The second thing I want to do is in front of the 2, or you could put it behind, but usually you see it written in front. We'll put a multiplication dot. You're going to put the first term in your sequence, and ours was 3. Now those 2 things go together. I mean, it's the same reason we did both of those features. What happens if you plug in n equal to 1? The exponent becomes 0. What is a value raised to an exponent of 0 equal? 1. So in essence, it becomes unimportant, right? This piece, when I plug in n equal to 1, becomes 1 because the exponent became 0. And then when I multiply it by the 3 at the beginning, I get 3, which is the first term I wanted. So what the minus 1 does at the top by the n minus 1, is it resets it to be the first term. So that when I multiply the number at the beginning, I get the first term. And let's check it for the second term to make sure it's okay. If I plug in 2, I get 2 minus 1, which gives me 1 as my exponent. So 2 raised to the 1 gives me 2. And then that 2 multiplied by the 3 at the beginning will give me 6, which is my second term. So the pattern always has n minus 1 as the exponent, and the first term is the multiplication factor in front. Always works that way. Okay. All right. Inductive or deductive? Is this reasoning inductive reasoning or deductive reasoning? Okay, so let's go back real quick where we defined them, because it's been several slides. Inductive reasoning is a method of making generalizations based on patterns or observations. Deductive reasoning is the use of mathematical axioms, theorems, definitions, or undefined terms assumed to be true in logic, and logic for proof. Yes. Which one is this? It's inductive. I took a pattern and I created what I thought was happening forever after that, right? Yeah. Even the forever after that, even if I don't do the forever after that, I did the next 3 terms. I assumed the pattern was going to continue in the exact same way, and I used that logic to create the next 3 terms. So this is inductive reasoning. Using patterns to establish what's going to come next, what's going to happen after that. Okay, let's do another example then. Kind of flipping the process around on this one. Using the nth term given, so now I have an nth term or a general term given, find the first 5 terms of the sequence, and then identify if it's arithmetic, geometric, or neither. Okay, so if I've got a general term, like I have here, and I want to find n equal, the first term, I set n equal to 1. So if I plug in n equal to 1, what is the first term for 5n plus 6 going to give me? 11. What's the second term? Plug in n equal to 2. 16. What's the third term? N equal to 3. 21. Fourth term? Do you see a pattern in what you're doing that will allow you to just write the next one down without plugging it in?
Adding 5 each time.
It's adding 5 each time. So the next one should be 31. And you might even not think of the adding 5. You might look at it and say, oh, look, I'm just going with all the 6s and the 1s in each of the number sets, right? So it's 31, 36, 41, 46, 51, 56, right? And that's what happens when I add 5. But you might also see it from a different sort of perspective in terms of the numbers you're seeing show up, too. Okay, so this is my first part, if you will. The second part was to say whether it's arithmetic or geometric, or neither. What's this one?
Arithmetic.
It is arithmetic, because we're adding 5 every time. Very good. Let's do it again. Step 2, or part 2, part B. What happens when I plug in n equal to 1?
Becomes 0.
It becomes 0. What about n equal to 2? 3. N equal to 3. 8. N equal to 4.
15.
And n equal to 5.
24.
24. Okay, so these are the squares minus 1. I mean, that's what it said right here, right? N squared minus 1. So I have 0, 3, 8, 15, and 24. Is it arithmetic, geometric, or neither? Arithmetic means I add the same number every time. Can I do that? No. Geometric means I multiply by the same number every time. No. The very fact that there's a 0 in it means it can't be geometric, right? Because if you multiply 0 with something, you get a bunch of zeros. So this one would be neither. Now I want to show you, however, there is another pattern involved in this particular problem. Before I do that, let's answer the question that's actually here. Is this inductive or deductive reasoning? It's deductive, because I'm given an equation and I'm told this is the pattern forever and always. Find some terms. Okay, that's deductive reasoning. All right, so just right here on this slide, you can do this right at the bottom of your paper. You're going to be given some patterns that will look like the 0, 3, whatever I've got going on here, 0, 3, 8, 15, 24. And sometimes you're not given an equation to figure out what's going on next. So I'd like to show you what it is you do in that case, or at least what you can try to see if it will work. All right, we're going to try it like it's arithmetic. What do I have to add to get the next term? And I know they're not all going to be the same, but we're going to write them down just because, okay? So 0 to 3, what would I write down as I add? 3. How about 3 to 8? 5. 8 to 15?
7.
15 to 24?
9.
Okay. Now, they're not all the same, right? I mean, they're not all the same number. But there's a pattern among them. If I do it a second time, how do I get from 3 to 5? 2. 5 to 7? 2. And 7 to 9? 2. So if I did sort of the arithmetic, looking for an arithmetic number twice, I found that they're the same. The first time I did it's called the first differences. So what do you think the second time was? Second differences. These have identical second differences. And whether or not you went to the point where you found second differences, or maybe you had to go to the third differences or fourth differences, eventually you'll either recognize the pattern or you'll see the plus 2's all matching, and you could find the next term in this sequence without an equation, right? You could. What would you have to add to 24 to get the next term? 11. So the next term should be 35. Also, that's because the 9 plus 2 is 11. That's why that's happening. Yeah? And you could check that because in this particular case, we do have the next, the equation's general term, n squared minus 1. If I plugged in 6, do I get 35? I do. I do. So that actually is the right process for finding the next term using sort of an arithmetic process to doing it. And what that's called is the second differences. But like I said, you could do it and you could extend it if you had to and look for third differences or a fourth differences, and we'll see that next time, not today. All right. I mentioned the word counterexample early on, like the second definition, if you will, of the day. What did counterexample mean?
Disproves a conjecture.
Disproving something. And it's a conjecture that is disproving something that somebody's guessing. All right, n plus 5 over 5. We'll talk about what and where this is going from part B, but the first thing on part A is to find a counterexample, an example that shows that this statement, n plus 5 over 5 equals n plus 1, is false. So, I'd like for you to take a minute on your paper, try some numbers. If you get a number that doesn't work, you're good and golden. I mean, like, that's it. You're looking for a number that doesn't work. A number that shows that this is false. So plugging in a number for n on both sides that shows then that the two sides don't, in fact, equal each other. Did you find a number that doesn't work, right, that makes both sides not equal? It's not terribly difficult to do for this one because most numbers don't work. Most numbers don't work here. What number did you try? Somebody give me an example. 1, 2, 4, 5. Fantastic. All those don't work. There's only one number that actually does work, I think. Do you know what number does work? 0 works. Yeah, 0 will actually make the statement true. All right, so we're going to do an example. I'm going to use 5. I like 5 because we'll stick with the natural numbers if I choose 5. So if I plug in 5 on the left, I get 5 plus 5 over 5. And if I plug in the number on the right, I get 5 plus 1. And the question is, I'm going to put a question mark above my equal sign, are they equal? So if I do 5 plus 5 on the left, what's 5 plus 5? 10. And 10 divided by 5 would be 2. On the right, 5 plus 1 is 6. So these clearly do not equal each other, right? Yeah. So this is called a counterexample. It's an example that shows that it doesn't work. Any idea why a student might think that these are equal?
Because 5 divided by 5 is 1.
Yeah. And you might actually see students doing something like this even. And they might decide that this is n plus 1. Or they might decide that it's equal to n. I've gotten that before too. The unfortunate thing is that we use the word cancel in mathematics to mean two different things. Sometimes we use the word cancel to mean it becomes 0. And sometimes we use the word cancel to mean it becomes 1. Reduces or divides or simplifies or adds to 0, those are more informative statements. But yes, you'll see somebody do something like this. There's lots of questions in your book where they'll have you try to give feedback to students, which is a good thing for you to practice doing. Because there's nothing more disheartening for you if you come to my office than me to say, because that's the way it is. Have you had a teacher kind of tell you something like that before? Because that's how it works. It doesn't really give you a lot of information, right? So like today when Vanessa came to my office, I'm trying to think of more than one way to describe it, right? Because if one way doesn't work and me restating that same way over and over again, then it's probably still not going to work. Same thing. So there's a couple of things if a student were doing this that you can address. Number one, I think it's a good idea to show them why it doesn't work with an example, a counterexample, showing them, well, check this out. It doesn't work if we put in the number 1. It doesn't work if we put in the number 5. So it must not be true in general. Okay, so there's sort of a see it doesn't work kind of issue. There's also more of an issue of what's going on really behind that, is that they're probably doing something like that we did on this, right? They're probably doing something where they're canceling out a 5 into the number 1. Well, what's wrong with that? Why? I mean, obviously it doesn't work, so why doesn't it work? What are they failing to remember?
You can't cancel out the 5 when it's being added to the n. It has to be multiplied by
Okay, so you might want to have issue with the fact that they're sort of ignoring order of operations, right? The addition on the top kind of is in a set of parentheses that you should do before you do the division. So that's one issue that we could address. What's something else you might address? What if they really do still really want to divide out the 5s? There's something else they could do to actually allow them to do that. What would they have to do? They could do this. Okay, if they did have an equation and they had something that was on a both sides kind of thing, you're right, they could. I think probably the way that the problem started out for a student like this, though, would be something like this. And for some reason, my pen's not working very well. They just started out with this only. So they didn't actually have an equation to start with. They actually had more of this is called an expression. Unless something already has an equal sign, it's not an equation. This would be an expression. And they were working with this expression and turning it into something else, okay? So if they already had another sided equation, they could multiply by a 5. That's true. If they really did want to divide out the n, what they could do is they could separate this into 2 fractions. Right? That would be equal. It would give them the 1 that they're expecting right here, but it would still leave the n divided by 5 at the front in a sort of a fractional notation. So that's another option. You could talk about the fact that, you know what, you're right, it does divide out, but it also has to divide the n, and you're failing to divide the n if you just only cancel it out with this piece. It has to divide both pieces, or it has to divide the sum of the pieces if you think about an order of operations. Okay? So when you're looking at questions in Part C, especially in your book, you need to be thinking both very concretely of show them how it doesn't work. That's what we did on Part A. And then also they explain why in general it doesn't work. Because some students really are going to be like, okay, I get the why it doesn't work. You told me why it doesn't work, but show me a number that it doesn't work for. And that'll work for them, okay? And other students like the show me a number is great, and they're good with that, and they're fine. But then there's some who are going to be like, okay, but why? But why doesn't it work? And that's useful information too.